Hello Science 30s. In this video we're going to talk a bit about series and parallel circuits, and we'll get into the differences between them and some of the properties of them as well. When you guys are drawing, first of all, on page 374 of your textbook, there is this diagram or this chart that will show you what to use in your diagrams. Okay, so wires are the lines there. Okay, wires joined, that type of thing. Okay, so use this, guys, to help you do your drawings. Okay, all right, so first of all, we're going to take a look at a series circuit. We're first of all going to talk about voltage, and then we're going to go into resistance. So first of all, with voltage, I want to first of all talk about what happens in a TI-83. So a TI-83, we got these four double or triple A batteries that are all in the battery or in the calculator. You take one out, obviously it doesn't work. And so every single one of these batteries is 1.2 volts. So that's 1.2, that's 1.2, that's 1.2, and that's 1.2. So we have four batteries that are connected in series. And the way that we would calculate the total voltage on this one is we would say we're going to call this V1, V2, V3, and V4. We're going to say that V total is equal to V1 plus V2 plus V3 plus V4, whoops, which is equal to 1.2 volts plus 1.2 volts plus 1.2 volts plus 1.2 volts, which is equal to 4.8 volts. So this circuit would get 4.8 volts. Now, what would happen if we put four batteries all together like that again, but this time they're in parallel? So I'm not going to write 1.2 every time, but we're going to assume they're all 1.2. We're going to call this V1, V2, V3, and V4. These are all 1.2, so that goes all the way along. We'll call this V5, V6, V7, V8. Now, what's the advantage of this? Do we get any more voltage? We do not get any more voltage. In fact, okay, the V total here would still equal V1 plus V2 plus V3 plus V4, which would also equal V5 plus V6 plus V7 plus V8. So obviously this is going to equal 4.8 volts. So why would we ever do that? Why would we ever have one line of series batteries up here and another line of series batteries here parallel to each other? The reason why is if this device took a lot of power. So for example, a laptop or a cell phone or something like that, you would want to have batteries in parallel because it would take longer for the batteries to burn out, basically. And now I want to do a couple examples with you guys to show you how to do resistance in series and parallel. So first of all, we have in this question, strings of small colorful lights are often used for holiday decorating and other occasions. An inexpensive string of these lights consists of 8 bulbs connected in series. The resistance of each bulb in the set is 64.0 ohms. So draw a schematic diagram of this circuit. So I've already done that. There's my circuits down there. You see the power source right there. It's not a battery, it's plugged in, so that's why it's a little bit of a different symbol than I used up top. And then I have 1, 2, 3, 4, 5, 6, 7, 8. And in fact, I'm going to go through right now and label these. My resistor 1, resistor 2, resistor 3, resistor 4, resistor 5, resistor 6, resistor 7, and resistor 8. Now, so this is the answer for A. B says if the set of lights is plugged into a 120 volt outlet, determine the current that will flow through the set. So now what we need to do is we need to figure out the current. Well, what do we need for current? For current, we need voltage. We have the voltage that's given to us, and we need resistance. We don't have the resistance. We need to figure that out. We know that each resistor is 64.0 ohms, though, and so my RT, my total resistance, will equal R1 plus R2 plus R3 plus R4 plus R5. I should have picked one with less numbers than this. R7 plus R8. Well, now I can just write this a lot easier though, because I know that each one of those is 64 ohms and there's 8 of them. So I can just go 64.0 ohms multiplied by 8, which is 512 ohms. And there we are. That's not the answer to the question. The question was asking us, what is the current? So now to figure out the current, what we need to do is, so there's my resistance. So let's just remind ourselves of that. That is equal to resistance. We have our voltage, which is equal to 120 volts. And our I is what we're solving for. V is equal to IR, which means that I is going to equal V over R if we divide by R on both sides. And so this is going to equal, what did I say? V over R, which is equal to 120 volts divided by 512 ohms. And that is 0.234 amps. Okay, what are the other questions here? Use your answer in part A to determine the current that will flow through the third bulb in the string of lights. They're in series, so the current's going to be the same. This is a series circuit, which means that it's going to flow the same throughout the entire circuit. So that's a trick question in a way, but it's a good question to see if you understand. And so the answer is going to be 0.234 amps, just like what we calculated down here. D, if the third bulb in the set fails, determine the effect on the other lights in the string. Again, we are in series. You disconnect one of those bulbs or one of them burns out, they all burn out. And that is definitely a disadvantage of having a series circuit. It may seem, you may be a store and be like, why is that set of lights so much more expensive than the other? Well, it does take a little bit more skill and work to do it in parallel, and so that's why you may see it that way. Maybe the cheaper one is in series, which will come up with a lot of headaches if you burn out a bulb. Okay, so that's series, pretty simple. The next question we're going to go over is this one. So a group of students is setting up for a high school dance. They set up some spotlights and other types of specialty lighting to help set the mood. 5 spotlights are plugged into a heavy-duty power strip, each light in its own outlet. Each of the spotlights has a resistance of 96 ohms. So A, explain why a power strip must allow parallel connections to each of the devices that plug into it. Well, in general, guys, one of the advantages of parallel is that each part can be controlled on its own. And so that would be why you would want to do that. So you can turn off one device, but it won't turn off all the others. So that's one of the biggest advantages of doing lights in parallel. Okay, there's my B. My B is right here. And so this is drawing a schematic. So there's my schematic right there. I have my power source right here because this is plugged in. I have 1, 2, 3, 4, 5 lights right there as well. Each one of these is going to be, what do they say, 96 ohms. And I'll give them names. There's R1, R2, R3, R4, and R5. So there's my 4 resistors there. And then now for C, they're saying if the 4th spotlight has 120 volts available to it, determine the voltage available to each of the other spotlights. And again, this is going to be in parallel. it is going to be the same. So every single spotlight will get 120 volts. And then for D, D is where we have to do the work, determine the amount of current. So this is a bit of a different formula. People who are not mathematically inclined will find this maybe a little bit tricky, but if you use your calculator properly, you will find this actually pretty easy. And so instead of it being just R1 plus R2 plus R3 plus R4, because they are in parallel, that's going to be 1 over RT will equal 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus 1 over R5. So we have these 5 and they're all in the denominator. They're all and we call that the inverse. So it's the inverse, and then each one of these is 96 ohms, according to the question. So what we're going to be doing here then, there's a number of different ways you can actually enter this into your calculators. So I don't know how to put a calculator into these videos, so I just have a picture of one. But this is the button you want to be using, is right there. Or you could use the division sign as well and just go 1 divided by and add it all the time. I tend to use this one. I tend to use the inverse button, x to the negative 1. And so the way I'm going to show you the way that would look on here, the way it should look on the screen. One thing I always do with this is I never put an equal sign over here. Don't do that, because what you're going to do then is you're going to forget that RT right here is in the denominator. So rewrite the entire thing. 1 over RT is going to equal 96 ohms is going to be 96 ohms. But then what we're going to do is we're going to take that to the negative 1. So in your calculators on your screen, it would just be without that ohms. So I'll do the next one without the ohms. It would look like this: 96 negative 1. Okay, plus 96 negative 1 plus 96 negative 1. That's 1, 2, 3, 4. We need one more. 96 negative 1. So then we have 1 over RT is going to equal, and again, depending on how you do this, but I mean, I'll just do this. Another way we could think about this is 5 over 96. If I did it with the 96 inverse, I would actually get 0.0520. Okay, now that we're at this point, there's two ways. Again, now I'm kind of showing this in two different ways now. Okay, what we can do is we can say, okay, 1 over RT. So 1 over RT is equal to this. So what I can do with this number now is I can say, okay, well then, RT, switch to my pen here, RT is going to equal 0.0520, and that's not finished. And that would be to the negative 1. So again, I would take that answer and I would inverse that answer again. And then I would get 19.2 ohms. And there we go. So that would be the total resistance in this circuit. Now, if I did it this way, where I kept it in fraction form, so 1 over RT is equal to 5 over 96, then this one might be a little bit easier to see what we have to do. RT, if we move that into the numerator, we just take the inverse of this. And so that's going to equal 96 over 5 ohms, which is equal to the 19.2 still. And there we are. That's how you're going to be doing series and parallel circuits. A lot more. We did a very brief overview of it today, but that's what we're doing. Okay. Have a good week, guys.